Okay, good morning, everyone, and welcome to week 5 of the fall 2025 Saturday Morning Physics program. We're here this morning with our friends at CERN in the CMS control room, and with Mike Wagman and Christina Wang. The session this morning is about the standard model of particle physics and physics at the Large Hadron Collider. So we're gonna have two talks this morning. So the software that we're using this morning is slightly different than what we use on a week-to-week basis. We, as always, encourage your questions, and we're glad you've been so wonderful about asking questions. But today they need to go into, instead of into the regular chat, they need to go into the Q&A box. You should all see at the bottom of your Zoom screen a button that says Q&A. Go ahead and put your questions in there, and we can relay them to the speakers. And Mike and Christina, let us know. I can put my hand up to let you know that we have a question. I don't know if you would rather take them at the end or if you would rather be interrupted. We can kind of play that by ear. But ultimately, it's up to you how you want to handle it. So with that, I'd like to introduce Mike Wagman. Mike has been a scientist in Fermilab's theory division since 2019. He uses very large computers to simulate very small particles in support of experiments at Fermilab and beyond. Mike graduated from Brown University in 2012 and got his PhD from the University of Washington in Seattle in 2017. He did a postdoc at MIT, where he was a Pappalardo Fellow in physics before coming to Fermilab. When he's not doing science, Mike likes rowing, hiking, yoga, and rock climbing. Take it away, Mike.
Okay, thanks very much for the introduction. I'm very excited to be able to talk to you about the standard model as soon as I can get my screen sharing working, which requires a Zoom restart. I'll see you in 10 seconds.
Uh-oh. Oh. In the meantime, thanks again, everyone, for being here this morning. Um, Looking forward to seeing everyone again. So next week we'll be back in One West in Wilson Hall at Fermilab for a regular session, and then the week after that we'll be at the Museum of Science and Industry in Chicago. So we'll send out more information on that at the beginning of that week. So okay, welcome back, Mike.
Thank you. And ooh, okay, can you see my screen now?
Yes.
Great.
Go ahead and shut my bit off.
Then, without further ado, let me jump in. So the main content of the standard model can be summarized in the fact that almost everything we observe can be attributed to four forces. You're probably most familiar with gravity. It's the force that keeps you stuck to the Earth instead of flying off into space. Electricity and magnetism are similarly responsible for keeping electrons stuck to atomic nuclei in order to form atoms instead of, again, flying off into space. And a key feature of electromagnetism, as the unified theory of electricity and magnetism is known, is that opposite charges attract, like charges repel. So this is what makes the negatively charged electrons stick to the positively charged nucleus. However, the nucleus is made up of protons that are all positively charged and repel each other. So from just electromagnetism, you'd expect the nucleus to be wildly unstable and split apart. The fact that it doesn't means that there's some additional force holding the nuclei together that's much stronger than electromagnetism. And since scientists try and keep names simple when possible, this has just ended up called the strong nuclear force. And as we'll discuss a little later, scientists have also observed radioactive decays and other nuclear processes that don't follow the rules of the strong force. And these demonstrate the existence of a so-called weak nuclear force that can, for instance, cause a neutron to decay into a proton, an electron, and a nearly invisible particle called a neutrino. So the standard model is a description of matter as elementary particles that interact with each other according to rules written in a language called quantum field theory. It includes 20 or so parameters, like the masses of particles, whose values aren't predicted by the model and need to be fit to some kind of data before you can predict other things. Okay, so we'll go around who are the particles in the standard model, what are the rules a little bit. But before diving into that, I want to take a step back and look at the process of building models in science in general. So all good model building should start with data. If you don't have data and observations to test your model with, then you can make up whatever you want, but you won't know how well it describes reality. Once you have data, you can start defining your model by including some sort of rules for how you want to describe your system evolving in time. Math is often a useful language for precisely stating these rules, but it's not the only option. In the standard model, the rules are written in a few lines of math that are small enough to fit on a coffee cup, but of course there's a lot of complication buried in what all of the symbols mean. The model should also have parameters. They could be universal things like the mass of an electron, or they could be system-dependent things. Like if you were trying to make a model of fluids, you might need to put in the boiling point as a parameter that's going to be different for salt water versus fresh water, and needs to be measured for whatever system you want to predict. Once you've defined a model and fit your parameters enough to describe some data, then you should think of it sort of like a hypothesis. And the next step is to test it. So you want to take your model and make predictions for things you haven't already measured, and then go out there, make new measurements, test whether the predictions were right. If they were, you can increase confidence in your model. You can't prove that it will be right in all other circumstances, but it was right in this one, and so you can gain confidence. And on the other hand, if you did make a wrong prediction, then you know for sure there's something wrong with the model. And you can go back and hopefully see what needs to be fixed or replaced and start the iterative process, the scientific method of building models, testing them with data, refining and you're improving your hypothesis to get it right. And in particle physics, this has been happening in the context of what we now understand as the standard model for over a century. So our journey really starts 100 years ago when scientists had recently discovered electric currents. And experiments at the time revealed something called the photoelectric effect, that when you shine a light source on a piece of metal, sometimes a current is produced. And to make this a little more precise, the light source needs to have a couple parameters. There's the frequency of the light, which just describes what color the light is. And then there's the intensity, how bright it is, how much energy it carries per time. And the electrons, if they're produced, will be described by some energy and some number of electrons coming off in the middle. And according to the classical theory of light a la 1900, the energy carried by the electron should depend on the intensity of the light, since this describes how much energy is coming from the light. A low intensity light source might take up a little while to build up enough energy to emit an electron, but eventually electrons should be emitted from any light source. And the problem with this is that that's not what was actually observed. So experimenters first noticed that whether electrons are emitted at all depends on the color of the light. If the frequency is below some critical value, then there's no current produced at all. And secondly, there's no time delay. When it does happen, the effect is virtually instant. And it's not clear how to square this with the model of light as this classical wave. And so Einstein made a radical proposal in 1905. The proposal is that light comes in packets. The energy isn't continuous, but it's carried in little packets of energy that we now call photons. And the energy of each light packet grows with the frequency. So Einstein's model has one system-dependent parameter, this W here, and it's the threshold telling you that when your frequency is not above some value that depends on your metal, nothing's going to happen. And this is what allows Einstein's model to account for the observations at the time that there is this sort of critical value in practice. And it also makes an important prediction. It says that the energy of the electrons should grow linearly with the frequency of the light, and the relation should be some fundamental constant that's the same for any metal. And this prediction can be tested. So 10 years after Einstein proposed this model of the photoelectric effect, Millikan published experimental results that agreed beautifully with Einstein's prediction. You can see the straight line fit to the data points there, and in the margins working out what the value of this each parameter is, which was found to agree with expectations based off other experiments. So this let us really conclude that light has to come in some sort of packet of energy in order to fit these explanations, and only 6 years after the experiment, Einstein received the Nobel Prize. He then went on to become arguably more famous for his theory of relativity, the first version of which was coincidentally also published in 1905, but those took much longer to test experimentally. And of course, Millikan's experiments 100 years ago are far from the only reason that we believe in photons. So technologies like night vision goggles and photomultiplier tubes used in modern scientific experiments rely intimately on the existence of the photoelectric effect and wouldn't work at all without the existence of photons. Things like solar panels and lasers similarly rely on properties of the particle nature of light, and our technologies are really built off this idea that light sometimes behaves like a particle and sometimes behaves like a wave. So some of the particles in the standard model have really come as surprises that weren't predicted at all. And famous examples of these happened in the 1930s when cloud chambers put at the top of mountaintops were able to take tracks of cosmic rays, particles coming in from space, and they discovered that some of them were the particles that we know and love here on Earth, like electrons, but this shows the image of the first antimatter particle ever discovered. And the reason why is that the chamber that this photograph is taken in has a magnetic field applied to it. And if you know the direction of the magnetic field and the direction that the particle is traveling, you can work out that the curvature of this track is exactly the right angle for an electron, but exactly the wrong sign. And so it corresponds to the motion of a particle with exactly the same mass of an electron, but the opposite charge. And no such particle was known to exist before these observations, but was immediately realized had to exist in order to explain them. So within a few years, we knew that antimatter existed, and there were also other surprises right around the corner. So in addition to the electron and the positron or anti-electron, a few years later, tracks were seen for particles that had the same charges as electrons or anti-electrons, but were about 200 times heavier. At first glance, these were thought to be the long-slot particle predicted to be associated with strong nuclear forces, but they weren't. They just happened to have the same mass as some other particle for what we think to be a coincidence. And so these were particles that really needed to be added to our description of the standard model because they showed up in the data and there was nothing we could do but expand our model to fit our observations. On the other hand, there are some particles that were predicted before they were observed, and seeing them really was part of what gave us confidence that our construction of the standard model was on the right track. So a few decades later, when scientists were trying to understand the details of the strong nuclear force, it had been proposed that protons and neutrons are themselves not elementary particles, but made up of smaller elementary particles called quarks. So we'll come back in a minute to what these quarks are, But at the time in the 1960s, there were three quarks that were hypothesized to exist, but there was only very indirect evidence for this theory of protons and neutrons being made of quarks. So, based off this theory, a couple of theorists in 1970 looked at observations about the weak nuclear interactions, the decay rates of various particles, and they realized that within our best understanding of the strong and weak nuclear interactions, if all the data was to be consistent, you needed a fourth quark. You couldn't explain all of the data with only three. A few years later, direct evidence was found experimentally for this fourth quark, dubbed the charm quark, that was found almost simultaneously at Brookhaven National Lab and at SLAC in 1974. So what's shown on the left here is a picture of plots of the original data from this 1974 experiment that are showing the number of particle production events as a function of the energy of a beam that was collided to produce these particles. And what you see is there's a big spike. Right around 3 in these units of GeV, you see that the number of events wildly shoots up. And this bump in the event rates is the signal that there's some new particle that you're producing whose mass is around that bump that can then decay into the particles that you see in your detector. And in addition to this evidence for the charm quark, a few years later, a fifth quark was discovered similarly, and 2 decades later, a sixth quark was discovered, both here at Fermilab. And the charm quark has now been studied extensively, so you can see a plot here from data at the LHC 10 years ago that sees the same bump around 3 GeV seen back in 1974, but now with the exquisite precision where the characteristics, the width of this bump can really be measured in beautiful detail and seen to correspond in detail to what was predicted from the quark models. Okay, so that brings me to the question of what these quarks are. Because some particles were discovered and then understood, some particles were understood and then discovered, some particles have been around for a long time, but it took a while for scientists to understand how they work in the language of particle physics. So before the theory of quarks was understood, there was a whole zoo of particles that had been observed in cosmic rays and produced in nuclear interactions that were thought to be elementary. And they have masses that are all different from one another and don't seem to follow any immediate rules. But when you look closer, there's lots of patterns. And these patterns and symmetries of the masses and other properties of these would-be elementary particles called hadrons were what led to the proposal of the existence of quarks. So a proton and a neutron were hypothesized to be made of 2 different types of quarks, often called up and down, denoted U and D. And then particles that looked kind of like protons and neutrons, except for some strange features in the observed data, were hypothesized to also be made of 3 quarks, but one of them was a different type called S for these strange properties of these hadrons. And Guillermo and other theorists were able to organize the strangeness and other properties of these hadrons in patterns that would make sense if you had them all coming from these 3 types of quarks. So this provided some circumstantial evidence for the quark model of the strong nuclear forces. It could explain these patterns in the data, but it was initially met with some degree of healthy skepticism since no one had ever seen one of these quarks in the wild. Our clear evidence that protons are in fact made of something came from accelerator experiments at SLAC in the 1970s, where high energy beams of electrons and protons were used to uh, make these maps of particle production rates, like I was showing for the charm quark a moment ago. And the surprising thing that was observed is that at lower energies, you saw all sorts of those spikes for different particles, this whole zoo of hadrons. But when you looked at collisions at even higher energies, they started to obey simple patterns that didn't make sense if protons and neutrons were themselves elementary, but were exactly what you would expect if they were made of some smaller constituent particles that behaved sort of like free particles at high energies. And theorists along the same time learned how to take the theory of quarks and include particles now called gluons because they glue the quarks together into these hadrons. And the theory of QCD, of these quark and gluon interactions, was able to reproduce the features seen in these high energy collider data. And part of the reason that quarks and gluons behave so differently from electrons and photons is that unlike in electromagnetism, where the force between two electrons will fall off as you increase the distance between them, the forces between quarks actually become stronger as you try and pull the quarks apart, and you'll eventually find that they're confined, that the forces become so strong that it would take an infinite amount of energy to pull the two quarks infinitely far apart, and instead they get stuck together. But the flip side of this is that the forces become weaker at the short distances probed in high energy collisions. And so when you look at data that characterizes the strength of these interactions, then it decreases as you increase the energy, with a trend across a variety of experiments that's exactly what's predicted by the theory of QCD. So the evidence then becomes more direct for the existence of quarks when we look at high energy environments, where we're able to view protons as three quarks that are bound together by gluons, and we can observe jets that look like individual quarks and gluons getting produced that eventually go off and turn into the particles that we measure in our colliders. And this shows some of the data from experiments at Petra, at Daisy in Germany in 1980, showing on the left here the tracks of energy coming from an event where two jets were produced. And this is what you'd expect if you had a quark and an antiquark that were produced and traveled back to back. The one on the right has apparently three jets. And an event with three jets is very hard to explain if all there is are quarks and antiquarks that have to be produced in pairs. So these sort of three jet events were what led to the sort of more or less direct observation that there has to be a gluon type of particle that can really be emitted in these jets. The hard part is that at low energies, protons look like a mess. They look like tangles of many gluons and quarks and antiquarks. And to make predictions for their low energy structure, you need numerical simulations that are often carried out in a framework called lattice QCD. And these simulations teach us that if you ask how the mass of a proton gets split up into the energy carried by the quarks and the gluons, then only around 1% of the mass of the proton actually comes from the masses of the quarks. The rest of it is all coming from the motion of gluons and quarks inside of these complicated bound states. Oh, I see a hand up, Spencer.
Yeah, so we have a question in the chat. I don't know if you would like to take it now or if you would rather wait until you're done. It's up to
Uh,
you.
sure, let's hear it now.
Sure. So the question is the increase in force between the quarks would sort of be akin to the elasticity in glue? Is that why that's so why they're so named, or is that entirely wrong?
Uh, yeah, that's basically right. You can also think of it as like a string. The force grows linearly, like if you had like a string or a spring that was connecting the two quarks. And this sort of language was actually the first place that string theory was introduced as a way of possibly describing that kind of uh, gluey confining force. Um, though that is a whole different story.
Thank you.
So, to try and understand these low energy properties of hadrons, there's been decades of progress in being able to perform these lattice QCD simulations that are able to predict the masses of not only protons and neutrons, but these strange hadrons that we see in cosmic rays. And we see beautiful agreement between the theory of QCD for these low energy properties of the strong nuclear force, as well as the high energy properties that we can see in colliders. And this begs the question then of how far we can go towards understanding nuclear physics, the emergence of atomic nuclei and chemistry with all of its complexity from the theory of QCD and the standard model of particle physics. And these are the sort of questions that I work on as a researcher. And it's a really fascinating field that requires a blend of pen and paper theory, but also high performance computing on some of the world's largest supercomputers in order to be able to perform accurate enough simulations to predict these properties of hadrons. And so research in Lattice QCD has really grown together with computing hardware from the first generations of supercomputers to the latest GPU machines like Frontier at Oak Ridge National Lab pictured here. And we're at a very exciting time where there's a lot of new technological advancements on the horizon related to AI, related to quantum computing, that could be the drivers of the next advances in our ability to really simulate the properties of complex systems starting directly from the standard model. And that's, I think, a really fascinating story that I'd be happy to talk to you more about. But the quarks and gluons are not the only particles in the standard model, and I should move along to cover the rest of the story here because there's
Re-
other fascinating chapters.
we do have one more question if this is a good
Oh yeah,
time for it.
please.
Let's see. When two hadrons collide, can the quarks mix, leading to two hadrons of quarks between the two of them, or does each quark only have two gluons unique to it?
Yeah, so when hadrons collide, the quarks get all mixed up with each other. And you should think of having of a proton as being made of three quarks plus some number of quarks and antiquarks that will be an equal number of quarks and antiquarks and kind of fluctuate around depending on the collision. And so you have the three quarks that are definitely there, but then also other gluons and other quarks and antiquarks that are produced during collisions. And so when two hadrons collide, you'll get these sprays of gluons and quarks and antiquarks that are all produced in addition to the net three quarks more than antiquarks that have to still be there at the end in the proton.
Great, thank you,
Yep.
and thanks for the questions.
Yeah, absolutely. Please keep them coming. And obviously these are complicated systems in detail that can only do so much justice to in a few minutes here. So don't be worried if it seems like there's more to the story. There certainly is. Okay. So, the other piece of the standard model that's really been a key piece of the history of particle physics in the second half of the 20th century has been our understanding of the weak nuclear forces, which really challenged science as demonstrating that sometimes you think you know the rules to build your models off of, and you're wrong. So theorists have asked for a long time. Okay, the ancient Greeks started asking centuries ago whether the world would act the same if you looked at it in a mirror. And by and large, people often tended to assume the answer is yes. It would just kind of be weird for it to be otherwise. And in the 1950s, two theorists, Li and Yang, tried to review all of the available data and see to what extent we actually know that that's true based on experiments. And they found that the data for electromagnetism and the strong nuclear interactions was pretty clear that you could do things that are functionally equivalent to setting up an experiment and a mirror version of the experiment, and they work the same to very high precision. But for the weak nuclear interactions, there really wasn't much good data about whether mirror versions of the weak force would work the same way. And so Li and Yang proposed that someone should go do an experiment to go test whether the weak interactions actually look the same in the mirror. Within a year, that experiment was performed, and the Wu experiment in 1956 demonstrated unequivocally that the answer is no for weak interactions. So the decays of an unstable nucleus that proceed by the weak interaction were observed very carefully in a detector that was able to tell what angles the particles were emitted at from the nuclei. And the experiment was able to find a clear preference that the particles that were emitted from these weak beta decays were always left-handed. So you should think of that being like if you have some particle that's moving in some direction, then it behaves sort of like a spinning top, and it could be spinning clockwise or counterclockwise. And what the Wu experiment showed is that the particles coming out from the weak interactions are never spinning this direction. They're always spinning this direction. And so this actually sort of solves one of the Greeks' philosophical paradoxes of how do you actually define what you mean by left-handed and right-handed if you can't just wave your hands? Like if you met some new alien species, how would you communicate whether something was left-handed or right-handed? And what this experiment showed is that you can use beta decays. The particles that come out from beta decays will always be left-handed in this certain sense. And this led to our modern understanding of how the weak interactions really work. And when theories were designed to incorporate this sort of parity violation, it came out that there needed to be additional particles in addition to the ones we had seen before, and there should be some particles that are associated with mediating these weak interactions the same way a photon is associated with mediating electromagnetism. And these got called the W and Z bosons. And the W boson is the one associated with these weak beta decays, hence the W. The Z is like a W boson, except it has zero charge for the Z. And so CERN accelerator experiments were able to directly produce the W and Z bosons for the first time in the early 1980s. You can see the image here of a Z boson event where the plot at the bottom is the energy deposited into different bins around your detector here. And what this is telling you is that all of the energy from this one collision ended up in exactly two bins that had equal energies. And if you add up the energies of these two bins, it adds up to exactly the mass of the Z boson that was predicted by the standard model of particle physics. And this was really a revolutionary moment for the standard model where predictions for some really complicated but fundamental properties of the weak force, like the mass of the Z boson, were really predicted theoretically before they were measured. And the world was waiting with bated breath to find out whether the standard model was going to be validated or totally falsified by these experiments. And the story goes that the Queen of England, in fact, requested that CERN wire her the answer to whether the standard model was right about the W and Z boson masses before the news was released to the public because she needed to know. So this was really a spectacular triumph of the standard model then when the W and Z boson masses came out as predicted. But there is still one key boson that was missing from the standard model at this point, or rather that's present in the theory, but hadn't been observed experimentally. And to explain the role of this Higgs boson, I need to step back just a minute to what the building blocks of these particles are in the standard model and how they're related to each other. So the quarks all come in what's called different colors that are what gets interchanged by the gluons. And the gluons really only talk to the quarks, but they talk to all of the quarks. The W bosons change what we usually think of as one building block into another. They can convert electrons into neutrinos. They can convert up quarks into down quarks. And so the building blocks here are arranged in rows that go along the particles that get connected by gluon interactions. The columns here are the particles that are connected by W's and Z's. But the building blocks for the left-handed particles and the building blocks for the right-handed particles are drawn differently and disconnected here. And that's for a reason, which is that when the world doesn't look the same in the mirror, the elementary left and right-handed particles need to be different. And the only way that you can start with different left and right-handed particles and end up with massive particles like we see is if you have some new boson. There needs to be something to enact the so-called Higgs mechanism or the Brout-Englert-Higgs mechanism, since there were several theorists who were on the cusp of realizing the same mechanism would work at the same time in the 1960s. And what Higgs in particular realized is that there would be this distinctive spinless boson with very particular couplings that would have to exist if this mechanism was in place. And work by Weinberg and other theorists soon after showed that you could get a viable theory of all of the strong and weak and electromagnetic forces if you take these quarks, electrons, neutrinos, the gluons, the photons, the W and the Z, and add at least one of these Higgs bosons in addition. And the simplest model that just has one Higgs boson is what we now call the standard model. So from its proposal in 1964, Higgs had to wait over, well, right around 50 years to see the actual experimental discovery of what was initially reported as a Higgs-like boson on July 4th, 2012. And this was a monumental occasion that I was one of many thousands of science aficionados who was up early watching the live stream of this discovery. in which there was an excess of events for producing two photons at a particular mass. It's not as vivid as the one for the charm quark, but you can see the bump here, right around 125 GeV, that signals the existence of some new particle. And with the first round of observations, all you can really say is that there's a new particle. It has these properties that sort of look like the Higgs boson, but a lot of the really impressive work that's been happening over the last decade at the LHC has been to understand whether this new particle actually has all of the characteristics that you'd expect if it was the standard model Higgs boson, or if it's something else, if it's the first one of two Higgs bosons in a twin Higgs theory, if it's the first of a zoo of particles in a supersymmetric theory. And you'll hear, I presume, much more about what's been going on in the LHC in the next talk coming up. But suffice to say, for these purposes, that heroic work over the last decade has measured an increasing number of properties of this Higgs-like boson, and so far they're all consistent with calling it the standard model Higgs boson so far. So this tells us that we have now all of the pieces of the standard model in terms of the forces that we need for how nuclei stick together, how they decay, how atoms stick together. And you might think then that we have all of the rules. And there was a time when scientists thought that maybe we did. But the world continues to be full of surprises. And so the last particle that I'd really like to spend a few minutes talking about here is the neutrino. So neutrinos are these particles that are produced in weak nuclear interactions. They're very hard to detect because they only interact with weak nuclear interactions. They don't interact with electricity. They don't interact with magnetism. They don't interact with the strong force. So you have to work to detect them, but they're produced copiously in the sun, which is itself a giant nuclear reactor. And so processes like two protons fusing into a heavy hydrogen nucleus that kick off the chain of reactions that power the sun release neutrinos. And so there's millions of neutrinos streaming through you every moment, since when the neutrinos are emitted from the sun, they interact so weakly that they basically just travel straight wherever they were emitted from, off into space. And some of them should reach us here at the Earth. So in the mid-20th century, we had some understanding that the sun was probably a giant nuclear reactor undergoing fusion that seemed to be the only way that it could continue burning and putting out this much power for billions of years without running out of fuel. But you'd like to test that theory. And one way to test it is by counting the neutrinos coming from the sun. Because by measuring the intensity of light that we see, you can make a good prediction for what are the rates of processes like these happening inside of the sun. And if you know the rates of these processes happening, then you know the rate that neutrinos are being emitted. And so you can predict how many neutrinos you should see if you could build a giant neutrino detector on Earth. And so that's what was done at heroic experiments in the Homestake mine in South Dakota in the 1960s. The neutrinos from the sun were detected, but at less than half the rate that was predicted by these theories of nuclear astrophysics. And so these were really hard experiments where you were taking close to a ton of liquid chlorine, sifting through it to look for individual atoms of something else that had been produced by a neutrino hitting the fluid in the detector every day. And so there were worries that there could have just been underestimated uncertainties in the experiments. Maybe the factor of 3 isn't so bad. There were worries that we don't understand something about stellar astrophysics. It turned out neither of those were true. We just didn't understand how neutrinos work well enough. And what was realized with decades of further neutrino experiments is that the original Homestake mine experiments were only sensitive to the kinds of neutrinos that should be emitted by the sun. But neutrinos actually come in three kinds. And well, although the standard model predicts that once a neutrino starts as one kind, it should stay as that kind forever, that's not what actually happens. It seems that neutrinos can oscillate between flavors mid-flight, so that what are produced at the sun are these electron type of neutrinos, but by the time the neutrinos show up at the Earth, they've actually transitioned into a more or less equal mixture of the three kinds of neutrinos, and so that's why the Homestake experiments only saw a third of the neutrinos they expected. So more recent experiments uh, at SNO and Super K were able to detect all of the types of neutrinos and show that indeed it's the right total number coming that you'd expect from the sun. It's just that they have oscillated into different flavors while they've been coming. And we now have a wealth of data from these oscillation experiments looking not just at neutrinos coming from the sun, but neutrinos coming from cosmic rays hitting atoms in the atmosphere, neutrinos coming from nuclear reactors, neutrinos coming from particle accelerators. And we've got a very consistent story emerging from the data that everywhere that we produce neutrinos, we produce them the way we expect, but then they oscillate and change their flavors between when we produce them and when we detect them. And the neutrino is therefore our one particle of the standard model that really breaks the rules of the standard model. We need to add some additional rules as well as some additional parameters to the standard model to account for these observations of neutrino oscillations. So that's why I said the standard model has about 20 parameters in the beginning, because how many you need in detail is going to depend on exactly how the neutrino sector works, and that's still kind of a work in progress. So here at Fermilab, we're designing and building what will be the world's most intense beam of neutrinos produced at Fermilab and then shot through 800 miles of rock, because neutrinos can just basically travel through matter, and aimed very carefully at the bottom of a mine, the same complex actually near Homestake in South Dakota, where we're going to be able to try and measure the oscillations of this super intense source of neutrinos to higher precision than they've ever been measured before, and learn things like whether the oscillations of neutrinos and antineutrinos are symmetric or whether there's violations in neutrino antineutrino symmetries that might actually give us big clues to what happened in the early universe right after the Big Bang. And there's lots more happening in neutrino physics. In addition, there's other oscillation experiments that are under construction and just starting up in China and Japan. And there's experiments searching for rare nuclear decays, something called neutrinoless double beta decay, that are actually testing whether neutrinos are their own antiparticles, and these are just different names for particles that could turn into one another. And so it's a really exciting time where we're full of new questions and lots of data and puzzles for theorists to understand how these particles at the edge of the standard model work. And the last point that I'd like to just close on here is that this very pretty picture of the Super K detector, which is this giant cavern, sort of like this from the outside, filled with water, is coated with detectors on the outside or inside of this spherical shell, uh, which are themselves photomultiplier tubes, which work because of the photoelectric effect. So we've come a long way from discovering that photons exist to building very fancy detectors where photons are part of the technology that we use to search for the next new particle. And this is really the story of science, is that we start with just mysteries and things we don't understand. We make measurements, we learn things, and then somehow it keeps turning out that there's practical things that you can do once you understand how the world works a little better. Okay, so I want to close with a couple questions, but was there one more in the chat before I come to these?
Yeah, there are two in the chat right now that I can read out.
Oh,
The
great.
first one is the first one's specifically about neutrinos. It's how do you go about detecting a particle that almost never interacts with anything?
Yeah, that's a great question. Um, and a large part of the answer is just that you need a really big detector, because the neutrinos almost never interact, which means they interact rarely, which means if you have enough detectors, you can see them interact sometimes. The other piece of it is that you need to be looking for a signal that can only come from neutrinos and really carefully shield out any possible backgrounds that could produce that signal. Then you just use your very large detector and wait for a small signal that you're sure has to come from a neutrino.
Excellent, thank you. Um, okay, we're getting more questions coming in now. Why don't I ask one more now, and then we'll save the others to the end. Is that all right?
Perfect.
Because I think you're getting close to your conclusion.
Yep.
Okay, so one more for right now, which is if the Higgs boson doesn't explain the mass of neutrinos, do neutrinos have right and left-handed components?
Thank you. That is a great question. That is one of the most open questions in particle physics, right? Uh, so let me just flash it up here on the slide. Are there right-handed neutrinos? I have no idea. We don't know. There might be, but we don't know yet. And that's, I think, a really fascinating piece of this story, is that we don't know if there are right-handed neutrinos, and we don't know whether neutrino masses come from the Higgs mechanism. They could come from different mechanisms. If you're interested in learning more about this, the word Majorana masses is the thing to Google. But let me just leave it as, really, this is a big mystery. There's different possible mechanisms for how neutrinos could get mass, and which mechanism is true really could be could be giving us a big clue as to what other particles and forces are out there beyond those we know from the standard model. So this diagram of the building blocks comes from a very recent online article by Chris Quigg at Fermilab that collects 100-some open questions about what's next in particle physics. And I'm just going to give you a taste of a few of them here. Um, but yeah, notice that this diagram tentatively includes right-handed neutrinos, because that was sort of the simplest building block you could add to give neutrino masses, but puts a big question mark here that we really don't know whether that's the right building block to add. Okay. Neutrinos are full of fascinating questions. They're not the only questions that we know we don't know. We know that there's some particles missing. We know that there is matter whose effects we can observe in astrophysics and cosmology that is not made of any of the quarks or uh, uh, particles that we can measure in the standard model. Maybe the right-handed neutrinos can be part of it. Maybe it's something else. And that's just a mystery. Perhaps even bigger mystery is so-called dark energy, which we know cosmologically needs to exist, but at this point isn't even clear if it is energy that should be associated with a particle or with something else. It's a big question mark. And even among the particles that we understand the basics of, I think there's a fascinating line of questioning in trying to push what we can do with the standard model. If we have our Legos, how far can we go in putting them together and assembling the building blocks to really describe the complexity of nuclear and atomic physics, starting directly from the standard model, and just pushing in our ability to simulate complex systems. And what often happens in physics is that as we gain the ability to predict more complicated phenomena, to be able to test more detailed features of our models, then this gives us new tools for designing new experiments, getting new ways to search for cracks in the standard model itself. So I think this question is very intimately connected to the other ones. Finally, there's also interesting questions about why the masses and couplings of the standard model are what they are. There's these 20 some free parameters. Why? Do they have some patterns? Is there some simpler unified theory that can predict why this zoo of seeming random parameters are what they are? Finally, I haven't talked about gravity since mentioning that it exists. And there's a reason, which is that at some level, the gravity can be incorporated into the standard model without any problems at an approximate level. You can include a graviton that, if you assume that gravity comes in packets of energy, much like light does, there should be a graviton, much like the photon. But at this point, we only have indirect evidence that gravity energy should, in fact, come in packets. And we know that if you try and ask questions about the quantum theory of gravity, sometimes it just breaks and gives nonsensical answers. So if you try and predict what should happen to a graviton as you push more and more energy into some space, then eventually the theory just breaks, and we know that we don't have the right description for describing gravity at those scales. So these are some of the puzzles that we know that we don't know. It's also worth emphasizing that the history of science has shown us that the world is full of surprises, and there are also lots of things that we don't know until we go out and find them. So I'll just leave this very incomplete list of questions here, and hope that some of these inspire some of you to think more and maybe go on and design the next generation of experiments, build the next model that will push the story of science further and give us answers to some of these questions. Thank you.
Thank you very much, Mike. That was fantastic. Wonderful talk, and we have several questions building up in the Q&A, which
Excellent.
I think maybe we'll read. I think one of them out now, and then if I think you are able to see the Q&A, and maybe you can type answers to some of them if you're able to hang on a little bit.
Yes, I will
Okay.
figure out how to find it.
Okay, so for right now, I'll just read out. So, do we think that neutrinos could possibly make up dark matter, given that they don't interact much with other particles? And is it a problem? Do they possibly not have enough mass to demonstrate the gravitational effects that we see from dark matter?
That's right. We know that the three neutrinos that interact weakly, the neutrinos that we can go out and measure, cannot account for dark matter. They don't have enough mass. They're too light to explain the gravitational interactions of dark matter that we know exist. The trickier question is the hypothetical right-handed neutrinos. They would not interact weakly. They'd be basically totally sterile and interact with nothing except gravity. And that could possibly account for some of dark matter, all of dark matter, but it depends on what masses the right-handed neutrinos have, if they exist, what their properties would be. So the weakly interacting neutrinos cannot be dark matter. If there are sterile neutrinos, maybe they're part of it.
Cool. Okay, so there are a couple more open questions, and then also there are a few questions that I tried to answer while you were talking. And you can also go look at those and perhaps add some more in case I've messed something up or didn't give a fully complete answer. But thank you again very much, Mike. Fantastic talk. So now we'd like to transition to Christina. Christina, are you ready to go? Are you able to share your screen?
Well, yeah. Yeah, let me try to share my screen.
Okay. Wonderful. Okay, so I would like to introduce next Christina Wang. Christina received a bachelor's in physics from MIT in 2018 and her PhD from Caltech in 2024. Christina is currently a Letterman Fellow at Fermilab, and her current research interests include high energy collider physics, axion and dark matter detection, and quantum sensing. So I'll turn the mic over to Christina, but please keep your questions coming in the Q&A box, and Mike and I will keep answering them. Take it away, Christina.
Okay, thank you. Thank you for the introduction. I think, yeah, I lost the Q&A box, so just let me know or speak up if you have any questions.
Yeah, I'll raise my hand if we have a question, and then you can decide when to pause, and I can read it out.
Okay, yeah. I actually have a quick question. Are they able to like unmute themselves? Because I have like
Unfortunately, they're not with this version
Okay.
of the Zoom software. Yeah, sorry about that.
Yeah, I have a little like exercise question, but we can see how we
Oh,
do
okay.
it.
Well, they can always put responses into the chat. Yeah.
Okay, yeah, so I will be talking about physics at the Large Hadron Collider. You've heard a lot about the development, the history of the Standard Model, and an introduction to almost all of the particles that we know have in the Standard Model. And in this talk, I will kind of talk to you about how we actually detect these particles at the Large Hadron Collider. So first, why do we even need a high energy particle collider? The simple answer is to kind of study the smallest things. And when I say small, I mean something that's smaller than an atom. So here you can kind of see a scale of things. So an atom has a radius of about 10 to the minus 8 centimeter. And the nucleus inside of it is about 10,000 times smaller than that, so about 10 to the negative 12 centimeter. And then inside of it, the nucleus of the different elements are made up of protons and neutrons that are about another factor of 10 smaller. And then within the protons and neutrons, they're made up of quarks that are another factor of 1,000 times smaller. So at the end, we have something on the order of 10 to the minus 16 centimeter. So these tiny quarks or these particles are what we're interested in. And essentially, quantum mechanics tell us that the particles are also waves at the same time. So the wavelength of a given particle with energy E can be calculated by this formula here. So it basically tells you, so that the H and C are constant. So it basically tells you that to be able to study things on a very very small scale, so a small wavelength, we need to go to a very high energy. So for a reference of the essentially the smallness of things that we're interested in, you can see kind of a scale of things that we're normally used to. So for our naked eyes, it's probably hard to see anything below on the scale of 1 millimeter. And then if we use microscopes, depending on the type of microscope, we can see things like bacteria that's on the order of 10 to the minus 8 centimeters, and the LHC, as I mentioned, is way down the line where we're expected to see something close to 10 to the minus 18. So something that's about 1 billion times smaller than a bacteria. So what exactly is high energy? So so the units that we're used to thinking about in high energy physics is electron volt, which is essentially the energy of an electron to gain over 1 volt, hence the name electron volt. And we're usually interested in things on the scale of GeV level, and that's roughly the weight of a proton. And what we do at the LHC is we collide protons at energies of about 13 TeV, which is about 10 to the 12 eV. And that's the energy that's high enough to help us probe the length of the scale of 10 to the minus 18. So I have this quick exercise. Maybe you guys can put the answers or any thoughts that you have in the chat. So a quick exercise is, so what do you think is the number of AA batteries that are needed to accelerate an electron to 1 GeV? And here are some couple of hints. So the first line tells you this conversion between electron volt and joules. And a typical battery, a AA battery, is rated at 2400 milliamp hours at 1.5 volt. And then the only equation that you'll need for this exercise is this equation here, the energy equals power times time. I'll give it a couple of minutes. Let's see if it works without interaction. And if you're confused about how to go about it, you can also put it in the chat. Okay, I see a couple of folks are a bit confused. Maybe I'll just go straight to the answer to explain the problem. And I also see a couple of answers, 1 million and 100 millions. You'll be surprised of what the answer is. First thing first, we want to convert the energy of the battery in units of joules, basically, or in units of EV, basically. So as I said, from this second hint here, one battery has 2400 milliamp hours, and we multiplied that by 1.5 volt. That's essentially the energy. That's essentially the energy of the battery, and then we convert this hour unit to second. This gives us about 13,000 joules. And then using this first conversion equation here, we can convert the 1300 joules to about 8 times 10 to the 10 eV. So one AA battery is much more sufficient to already accelerate an electron to 1 GeV. So I just said that the LHC accelerates particles to about 13 TeV, which is still less than what you're seeing here. But now that we're saying that one battery has much more energy than the LHC, what are we missing here? So that's a bit counterintuitive, but one thing for sure is that at the LHC, we're accelerating single protons to that energy, while in this battery, these are all macroscopic energies that are stored by trillions of protons and nucleuses in the battery. And also, whoops, I missed the animation. So additionally, it's extremely hard to accelerate the particles at high energy, because when the particles are accelerated to a speed that's close to the speed of light, their kinetic energy increases, but also their effective mass also increases. So essentially, they get heavier and heavier as we accelerate them close to the speed of light. So as they become heavier, it's even harder to continue accelerating them. So from this equation here, you can see that this is essentially the equation for their effective mass. And you can see that this increases as the velocity of their particle increases. So to be able to accelerate particles to higher and higher energies, we need stronger and powerful magnets to be able to provide the powerful electromagnetic field to accelerate these particles. So that's basically exactly what the LHC does, which stands for Large Hadron Collider, to accelerate protons to about 13 TeV. So it's a huge circular collider with a circumference of about 27 kilometers. So here you can kind of see where the ring is about on this picture of the France and Geneva border, or France and Swiss border. It's about 100 meters underground, so it crosses the French Swiss border. So this part of it is roughly in Switzerland, and here you can see the Geneva Lake, and this is where Geneva is. And then the other half of it is in France. So CMS is in France, while Atlas is in Switzerland. So this collider is hosted by CERN, which is the European Center for Nuclear Research, which is a lab for particles physics, similar to how Fermilab is the US lab for particle physics. So inside the LHC, there are actually two separate rings where two separate proton trains of proton bunches circular in this rings. So one in clockwise direction and another one in counterclockwise direction. So that allow us to collide the two proton trains at different collision points. However, the protons within each ring, the protons are essentially not a continuous stream of particles that occupy the entire circumference at the same time. They're grouped into different bunches that are about 7.5 meters apart. So at a given time, given the 27 kilometer circumference and that each bunches are about 7.5 meters apart, at any given time, there are roughly about 3,000 bunches in the ring that are being accelerated. And within each of these bunches, we have about 100 billion protons that are within each bunch. And then they get injected to the LHC and they circulate the ring for about 20 minutes to get accelerated to the target of about 7.5 TeV. And when two of these proton bunches collide, the energy of the two bunches get summed, so the total energy of the collision energy is about 13 TeV. And when the bunches crosses, it's actually the partons or the quarks that are within the protons that would interact, and usually these partons carry about a fraction of the proton's energy. So there are four collision points at the LHC, or four main experiments that are located at different points on the circular ring. So the first one is called ALICE, which it stands for a Large Ion Collider Experiment. It studies the collision of heavy ions, so like lead, that allow us to create a state that resembles the conditions right after the Big Bang. And another one is called LHCb, where they're particularly interested in studying heavier quarks like the bottom quark. But I'll focus more on the two general purpose experiments today, on CMS and Atlas. And you can see here they're located on kind of the opposite end of the circular rings. So what does it mean to be a general purpose particle detector? It essentially means that we try to build a detector to try to study almost everything that comes out of the proton collision. We want to collect as much data as possible to allow us to measure the properties of the particles from the standard model that we already know. So the ones that you've heard from Mike, we want to be able to measure. So usually after we discover the particles, we want to measure, take as much data as possible and try to measure the properties of these particles. So for example, the mass of the particles, or how they decay, and the other kinematic properties of these particles. Because as we improve on the precision of our measurement, we may be able to see indication of things that we might not know before. You could think of it as if you're improving the resolution of an image that you've taken, and as you improve the resolution of images, you can start seeing substructure of things that you might not know exist before. And we also, in addition to carefully studying things that we already know, we also want to look for new particles that we have hints for that may exist, for example, like dark matter, or we could also look for things that we don't even know exist already. So to be able to achieve all of these, we want to make sure that once these particles are produced, once the proton-proton collide and produce these particles, our detectors allow us to detect them efficiently and also identify them correctly. And in addition, we want to measure the energy and momentum of these particles precisely to help us reconstruct what exactly happened at the collision events. And so here at the bottom, you can see a picture of a slice of Atlas on the left and CMS detectors. So, so what particles can we detect? So our detectors are shaped essentially like an onion. So where we have detector layers that are wrapped around the collision point. So we try to detect any activities of particles that come out of the collision. So the types of detectors that we can identify and detect depends a lot on the lifetime of the particles. So if the particle has a short lifetime, as you can see from this little diagram, then it's likely that they will immediately decay into other particles before ever reaching even the first detector planes. So for example, the Higgs and the WZ bosons are all examples of these short lifetime particles. And then in addition, we also have particles with medium lifetime. They could have lifetimes of about a few millimeters or up to meters. And they may decay inside of our detector. So after passing through a few layers, as you can see from this little schematic, they may decay to other particles. And then in addition, we also have stable particles that can travel through the entire detector. And I'll go through each of some examples of each of these particles with different lifetimes in the next few slides. So for shorter lifetime, so here you can see a diagram of the particle mass on the y-axis and then the particle lifetime on the x-axis. And these are all examples of particles in the standard model that we know of. So for shorter lifetime, so below 10 to the minus 5 second, we have particles like top quark, Higgs, as I mentioned, Higgs boson, W and Z bosons, essentially these particles decay immediately after they're produced for the length scale that we're able to detect. So you can see here we also have lines where we convert the time into distances. So you can see all of these particles will travel less than 1 micron before they decay. So we won't be able to differentiate anything lower than 1 micron. So in a sense, for a detector, it's essentially an immediate decay. For these particles, we detect instead of the particles themselves, we detect the decay particles, and to try to reconstruct what the properties of these particles. And I'll also go through these in detail a bit later. So sorry. One thing I forgot to mention is we also have a bunch of, in addition to the top Higgs W and Z, we also have a bunch of hadrons at the bottom with smaller masses, but they also have a prompt lifetime. And I think this was already explained in Mike's talk. Hadrons or quarks and gluons do not like to be alone. They get bunched together to form hadrons due to the strong interaction. So in our detector, the high energy quarks and gluons quickly get bunched together to form a spray of hadrons that we essentially call jets. And in our detector, we cannot differentiate the individual particles within the jets. So we essentially see them as one coherent particle, as a shower of particles in our detector. So moving on to medium lifetime particles. So for particles that have a medium lifetime, or if they travel for a distance of between about millimeter to 10 meters, they would essentially traverse some detector layers and then decay in the middle of their detector. And then we have stable particles like muons, electrons, photons, and also some hadrons. For these particles, they would traverse through our entire detector, which is on the size of about 10 meters. So for our detector, if it's more than 10 meters long, then it's considered a detector stable. And our detector is mostly optimized to detect stable particles out of all the particles that we just looked through, and these objects can be used as building blocks to reconstruct any other type of particles. And also by analyzing the topology and the relationship between these particles, it can help us reconstruct the entire collision event.
Christina,
Mm-hmm.
we have a question in the chat. Is there a correlation between the mass of a particle and its lifetime?
Not necessarily. That's why you don't see a clear trend here. If it were, then we would see a clear trend where there's either a positive or negative correlation. So we have particles that are essentially everywhere on this plot. So yeah, so there isn't necessarily a correlation between the mass and lifetime.
Okay, thanks very much.
Yeah, so thank you for the question. So if you have more questions, please keep coming in.
Okay, there is one more that just came in. Does the presence of other particles change the stability of? So in other words, can particles interacting with each other change the stability of either of them?
Yes, yeah. So I guess, yeah. So I guess I guess how often or how easily a particle interact with other particles essentially determines their lifetime. So for particles that rarely interact with other particles, for example, like pions here, or if it's either because they rarely interact with other particles or because it's kinematically harder for them to interact, they generally will have a lifetime. So basically, the longer lifetime tells you it's they rarely interact with other particles, and shorter lifetimes tells you that it interacts with other particles more often.
Great, thank you again very much.
So let's move on to how do we actually measure and detect the particles with our detectors. So we'll start with by just designing like a baseline LHC experiment and Atlas or CMS. They're both kind of designed with the same concept in mind. Designing a particle detector is kind of like playing a Pokemon. We need to try to catch everything that comes out of the collision. And you could also think of it like building a camera where we take a video of the collision event and we try to reconstruct what particles come out of the collision, which direction these particles fly out, and how fast they fly out. And the more particles we can capture, and the more resolution we have in our camera, the better we can understand what's happening during these collision events. So first thing first is we want to make the detector hermetic, meaning that we want to cover as much angle around the collision point as possible. So essentially we build a cylinder around it. So we do know that most of the activities that we are interested in are centered in this plane. So we usually call this this axis, this horizontal axis, that the proton coming in, the z-axis. So we know that everything or most interesting things happen at around z equals 0. So we make the cylinder or the circular part kind of around the collision point that we know we're more interested in, and then the cylindrical part is not. The simplistic picture is it's a cylinder, but in reality there's a little cone-shaped region here that's empty that allow the proton bunches to come in. So then after we know what shape of detector we want, we need to build a magnet in the detector to bend the charged particles that will allow us to measure the momentum and the momentum and the particles precisely. So if we provide a magnetic field that is perpendicular to the motion of the particles, then we know that from E&M that the magnetic field will provide a force to bend the particle trajectory. And you can see from this equation here that given a constant magnetic field, B field, the radius is essentially proportional to the velocity of the particle. So the larger the velocity or the momentum of the particle, the larger the radius will be, and the more straight the path of the trajectory will be. And on the other hand, if the velocity is small, the radius will be smaller, so the resulting path of the particle will look like they're more curved. Since our detector is built in a cylindrical shape, we also want our magnet to be built in a cylindrical shape and provide a uniform B field within this cylindrical volume. And a magnet that is in cylindrical shape is essentially a solenoid that provides a uniform magnetic field in the z direction of the detector. So then given the magnetic field and given that it bends the particle trajectory, how do we measure this particle trajectory? So we do so with a tracker, and the tracker is made of tiny pixels, just like our camera, and each pixel will register the hits from the charged particles. And then we build many layers of these pixels, as you can see from here, along the path of the particle trajectory. So the particles, as they traverse through these layers of pixels, they will leave hits in each of these layers. And then by connecting the dots from each layer, we can create a track. And the requirement of the track is that they must be lightweight, meaning that the amount of material in each of these layers must be small, so that the particles don't lose too much energy or momentum by interacting with the tracker material. So if you imagine if the tracker material is too thick, the particles might be stopped by the tracker. And these tracker are typically made of the silicon detectors. So other than velocity and momentum, we also want to measure the energy of the particles. which we call calorimeters. So the calorimeters need to be, so the trackers are made of thin, lightweight materials, but on the other hand, we want the calorimeters to be made of materials that are exactly the opposite. So we want the calorimeters to be made of dense materials to completely stop and absorb the energy of the particles that slow down because of these dense materials. So that would allow us to measure the amount of energy deposited in the detector for higher momentum particles that have higher velocity. So the kind of analogy is that if you have a baseball coming at you, we catch and stop the baseball. And then to stop it, you'll need to exert some amount of force, and you'll feel that the baseball is hitting you when you stop the baseball. And by judging the amount of force, the faster the baseball, probably it hits you harder. And then by judging the amount of force, you get a feeling of the velocity of the particle. And that's exactly what we're doing here with the calorimeter. And then at the very end of our detector, we have our muon detector. So I don't know if you still remember, but muons are one of the more stable particles. And also another interesting feature is that muons are decay products of many interesting particles like the Higgs boson and the Z boson. And since they travel all the way through the detector, they leave a very distinct signature that is hard to miss. And the muon system is very similar to the tracker. It also registers and records the hits from the muons as they pass through. So they give complementary information to the tracker. And here you can see a little cross-sectional view of the CMS detector, where for a muon, it would leave hits in the tracker region and also in the muon system at the very end. So by connecting the dots in the tracker and the muon system, we can detect the muons very efficiently. And so putting it all together, the CMS detector has a cylindrical design, as I mentioned. It's about 15 meters in diameter and 21 meters long. It has a solenoid that provides about 4 Tesla magnetic field throughout. So here you can see a slice of the CMS detector. So this blown up version is essentially a one angular slice in the cross-sectional view. So the left-hand side here is the interaction point, and we'll have particles that get produced at the interaction point, and then they fly out radially towards the end of the detector. So from left to right, you can see that we're going radially outward, and the scale here, you can see that the radius of our detector is about 7 meters. So in the most inner detector is, as I mentioned, the silicon tracker that record hits from charged particles. And then behind that, we have the calorimeters that will stop the particles to record the energy of particles. And most particles will be stopped by the calorimeters, and the only particle that is not stopped by the calorimeter is the muon detector to record. And so essentially the only standard model particle that will reach the muon system are muons. So the amount of data that we produce at the LHC is enormous. The collisions happen every 25 nanoseconds, so essentially 40 million times every second. And the raw data essentially contains the hit level information from all the channels in all the detectors that you saw within that 7 meter radius and 15 meter in length. So that's roughly about 1 petabyte of data per second, which is of course impossible to save all of them. So we have a trigger system that help us filter down or choose only the interesting events to save. And due to the limited storage space, we only choose about 1 in a million collisions to save at the end. And even with that, it filters still down to about a few gigabytes per second. And in comparison, TikTok and Instagram is about 10 terabyte of data per day from users. So it's comparable to the amount of data that's produced from these social media softwares. So now let's use our particle building blocks and the detector starter kit that we just went through to try to reconstruct a Higgs boson. So a little introduction of the Higgs boson. So there are many ways that the Higgs boson can decay, and it almost include every kind of particle or object that we just went through. They mainly so from this pie chart you can see that they mainly decay to a pair of BB bar. So 58% of the time, and the B jets, the B quarks will hadronize into jets. And additionally, the second largest decay mode are a pair of W bosons that then mostly also decay to jets. And similarly for taus, they also decay hadronically to jets. And so, in fact, the most important decay modes that we that have been useful in the LHC experiments are actually these two decay modes that contain a very small fraction of the decays. And as I mentioned earlier, our detectors are really good at measuring things like muons. So then for this Higgs to ZZ decay modes, we mostly look for Higgs decaying to a pair of Z bosons, and then both of them decay to muons. So essentially, in the final state, we essentially have the Higgs decaying to 4 muons, which is a very distinct signature that other processes don't really make. So that makes it very easy to distinguish these processes from other background. And additionally, we're also very good at detecting photons. So even though both of these compose a very small fraction of the possible decays, these are the two decay modes that we end up learning the most of what we know about the Higgs. So here I'll show an example of how we reconstruct the Higgs boson. So considering the Higgs decaying to a pair of photons, we use the calorimeter to measure the energy of the photons precisely. So each of them will decay so the Higgs decays to 2 photons, and each of them will be captured by the calorimeter. So we denote it by E1 and E2. And then we'll also know where the energy deposits are, so we can measure the angle between the 2 photons quite precisely. So from these essentially 3 measurements, we can calculate the mass of the 2 photons. And if the 2 photons come from the Higgs, then the calculated mass should be roughly about 125 GeV. It's not going to be exactly 125, a delta peak at 125 GeV, since our detector is not perfect. It's going to be roughly a Gaussian distribution that peaks around 125 GeV. So if we plot the diphoton mass, then for background, which is shown on the left, we're going to see some flat distribution from random background, while for the Higgs that we're looking for, we'll see a little peak at around 125 GeV. And so this is actually what we saw in 2012. This is a plot from Atlas. Just like what I showed in the previous slide, for background, we'll see a roughly flat distribution, and we'll see a little peak at around 125 GeV. It's not from the top plot, it might not be as obvious, but if you look at the data subtracted by the background, you can see clearly we see an excess of events at around 125 GeV. And Peter Higgs, whom the Higgs boson was named after, was awarded the Nobel Prize in 2013 for predicting the existence of the Higgs boson. So what's next for the LHC community? The LHC community is preparing for an upgrade in the next few years that would allow us to take data even faster at about 7 times the speed that we're able to take data today. We plan to collect 20 times more data by 2040, and we're currently improving both the Atlas and the CMS detectors to be able to handle such a large amount of data and a large flux of data coming in at a very fast pace. And with the new data coming in, we'll be able to detect more Higgs boson to measure its properties more carefully. And that will also potentially allow us to discover unknown beyond the standard model particles. So there's a lot happening ahead of us with a very interesting and bright future. So that's all of my slides. I want to thank a number of postdocs who have given this talk in the previous years for providing the materials and valuable input for this talk. Yeah, thank you.
Thank you, Christina. Excellent. Very, very well done, and thank you for such a fantastic talk. We have two questions in the Q&A right now. I'll go ahead and read them out to you. But other folks, if you want to put more questions in, please do. This is the time. So the first one is, if particles always decay into other particles, and they all have different masses and a variety of properties, and all of their masses are connected to how much energy they have at any given time, how do we know, or why do we think that the particles that we've identified in the standard model are elementary particles?
Yeah, that's a great question. So I think when we say decay, it doesn't necessarily mean that the decay particles, like let's say the Higgs decaying to a pair of photons, it doesn't really mean, I guess, in a classical way that the Higgs is made up of 2 photons. It really just means the Higgs interact with these, and then it couples to these particles. So both of them are elementary particles in a sense that the Higgs are not composed of other particles. It just means that they interact. I don't know if that answers the question.
I think so. I think it's related to the next question, actually. So I'll go ahead and read that one. Did scientists predict a stronger signal to noise ratio for the Higgs boson peak at 125 GeV? The questioner says the signal seems relatively small on the bump or shoulder. Not sure how the observed signal to noise compared to the prediction. So I guess it's kind of a question about what we predict as far as our detectors and what kind of signal we expect them to give us.
Yeah, so so I guess the signal to noise ratio that we observe is what's being predicted. It's usually small at the discovery because we usually claim discovery when the signal when the significance is above 5 sigma. But over time, as we accumulate more data, this peak will be more prominent.
Great. Any other questions for Christina? We'll leave that open. I know it takes a second to type, but I guess we're maybe slightly ahead of schedule. I don't know if our friends at CMS are ready to start the tour here in a couple minutes, or if we should take a little break.
I think we should take a little bit of a break.
Okay,
if it is fine for you.
Sure. So right now it is. I'm sorry.
Oh, sorry. It's I'm talking about 6 p.m. in CERN time.
Oh, okay. That would be a 15-minute break.
Yes,
would it be
exactly.
possible to start maybe a little earlier? Maybe make it a 10-minute break and start at 5 till the hour, or do we if we need to?
I would propose the 6 o'clock.
Okay,
rather.
very well.
15 minutes break. All right, thank you.
All right. Well, let's. So thank you again, Mike and Christina. So right now we're going to take a break, and we'll please try to be back at 2 to 3 minutes before the hour. It's currently 10:45 a.m. Fermilab time, 5:45 p.m. CERN time. We'll reconvene. Let's say in 13 minutes or 12 or 13 minutes, so that we're ready to go with the tour at 11 a.m. Fermilab time, 6 p.m. CERN time. Thanks, everyone. See you back here in a few minutes. Thank you. Okay, I hope people are coming back on. It is 10:59 in Illinois and 5:59 in at CERN.
Yes, one of our guides is already here. If we can wait another minute or two.
Yeah, of course.
Great. Okay. All right. Thank you.
Yep. I'll leave it to you to start it up whenever you're ready.
Okay.
Thank you.
Derek, we are ready to go. No, sorry, Spencer. Oh, Derek, we are waiting for. Spencer, sorry. We are ready to go.
That is fine. Okay, well, thank you very much. Welcome back, everyone. Our friends from CMS are going to give us a virtual tour of the detector, and I will please begin when you're ready.
Okay. Hello. Welcome to CMS. So we are in the CMS control room right now. My name is Andres, and I will be one of the persons showing you and talk to you about CMS and DLHC and whatever else you might want to know about. So you're welcome to ask any questions in the Q&A, and we will. I see there's a few questions already, and some have been answered. But we can, of course, answer some of these questions as we go along. So I am here with Zoltan and Noemi, who are the coordinators for this sort of virtual visit. And many thanks to them for making this happen. So should we go ahead and start?
Yes, I think we can.
Okay, so I think we can show a few slides just to give you guys a bit of context. And then we will go to the underground areas. Unfortunately, at the moment, we cannot access the detector. There's no beam in the machine, but beam is expected to be back relatively soon, and it's not enough time to have access to the detector. But we will show you the underground areas, and yeah, I think we can start the screen sharing just to show a few slides.
Yes, of course.
All right. So this is a photo you may have seen before, perhaps. So this is a view from the Jura Mountains looking over the Geneva area, and you can hopefully see the lake here. This is the Lake of Geneva, and you have the Salève Mountains just a bit further back, and then in the far back, that's the Alps, and that's Mont Blanc over here, the tallest mountain in the Alps in Europe. And you have the border also. So you can see Swiss and France. The border actually cuts across the LHC tunnel. And so it's sort of very often we cross the border. So I live in France, for example, so I cross the border every day to get to CERN, to the main site. And so the main site of CERN is here. That's about relatively close to the airport. And it's about 20 minutes or so from the city of Geneva. And you can see that there are a few, so this of course represents the LHC ring. It's 100 meters underground, but we are actually in CMS, so we are pretty far away from the rest of the, let's say from the main site of CERN. So that's about a 15 to 20 minute drive from where we are to the main campus at CERN. Okay. So here's a different view of the infrastructure at CERN and the accelerator complex itself. So there's a lot more going on than the Large Hadron Collider. There's many accelerators, some of them very historic. So there's, for example, the proton synchrotron from 1959, and that's still in operation now. Of course, it has been upgraded. And then we have the super proton synchrotron. So they built a bigger proton synchrotron. I call it super. So the super proton synchrotron was, at the time, it was colliding protons and antiprotons, and it was I think at the time, it was the most powerful accelerator of its time. And this is where the vector bosons, the Z and W bosons, were discovered, and a Nobel Prize was awarded in 1984, if I recall correctly, for the work associated with that discovery. And then we have the Large Hadron Collider. So Large Hadron Collider is 26.6 kilometers in circumference. That's, I think, in American units, is like 17 miles, I think. And yeah, I also wanted to mention there's a lot of history, but there's also a lot of projects and experiments that are unrelated to the LHC. I'll just mention one. There's the anti-proton decelerator, and this is also referred to as the antimatter factory. So this is a very interesting, it's actually a facility where there's many different experiments associated with antimatter, and this is where we can, at CERN, produce anti-hydrogen and study it. Let's put it that way. Okay, so here's a view of the underground areas, and when it comes to the LHC, and also you can see the SBS, this is basically all underground. The Large Hadron Collider is roughly 100 meters underground. So where we are here at 0.5, you can see some of the, there's a few shafts, and we'll get to see the main shaft, and you'll look at especially the elevator shaft. And here in CMS, it's 98 or 97 meters deep. But then if you go to 0.4, where we have the accelerator cavities, it's deeper, but not exactly, it's not that it's deeper, it's just that there's mountains on top. So it turns out to be about 140 meters deep. But it is actually the case that the LHC tunnel is tilted by about 1.5 degrees, if I recall correctly. So it's not perfectly level with the ground. But generally, we can say it's about 100 meters deep. And so we have 4 large experiments at the Large Hadron Collider. Of course, we will focus on CMS. We have a sibling experiment, if we can call it that, the ATLAS experiment and the ATLAS detector, and the collaboration, the ATLAS collaboration, does similar work as we do in CMS. So it's a bit of a rivalry, if you will. So we want to have better results and want to have them out faster than Atlas. But we do mostly general physics, let's say physics analyses. So we study very much the same kind of things, and it's very important to have this this model where we have 2 experiments that can do the same science. Just to give you an example, in 2012, we announced the discovery of the Higgs boson, and that was announced simultaneously by both experiments, and it really adds to, you could call it not exactly reproduce, well, yeah, it is reproducibility of the results, where you have 2 collaborations that independently have analyzed all the data and reached the same exact conclusion. That really reinforces the result, the reproducibility, and the significance of the result. So I will just quickly also mention ALICE and LHCb. ALICE is a more, let's say, dedicated, its purpose is really to study heavy ion collisions. And almost every year, for between 2 to 4 weeks, we have the heavy ion program. And so in these periods, we're colliding typically lead ions. So that means we take lead atoms, we strip all the electrons, and they circulate around the LHC, and they collide in all 4 experiments. All 4 experiments participate in the heavy ion program, but ALICE is specifically sort of designed and specifically studies these kind of collisions. And then we have LHCb, which is a really interesting detector. It's asymmetric, which is one of the more striking things about it. And this detector is the collaboration mainly is interested in what we call flavor physics, or B-meson physics, which we can discuss later if you're interested. But everything, you often hear that they're studying the symmetry in the universe, or the symmetry or the asymmetry between matter and antimatter. Okay, so let's talk a little bit more about CMS. So here is let's say a figure of the underground areas. I think I'll come back to that once we're underground. I just wanted to show you guys a little bit about CMS, and then we'll get started. So here we have a picture of CMS where somebody has taken a bite out of it, and we often say that CMS is like a cylindrical onion. We have cylindrical layers inside of cylindrical layers.
Not stinky.
Not stinky. It doesn't smell bad. And so CMS is, I think I would describe it, if I have to be very quick, I usually say that the main element in CMS, I would say, is the magnet. So we have a very large solenoid, and this is a superconducting magnet that is 6 meters in inner diameter and about 10 meters long. And most of our detector, if you don't include muons, then all of our detector fits inside of this magnet. And we have two types of systems generally. We have what we call silicon trackers, and then we have the calorimeters around them. So generally the blue areas are the silicon trackers, and then in yellow you have the calorimetry, more or less. And so I will come back to these two types of detectors and just mention that outside of the magnet, everything you see is dedicated to the measurement of muons. So muons are, they're basically the same as electrons, but they're about 200 times heavier. And these are really central to a lot of the studies that we do in CMS. And so when you put all this together, it's in the name, right? It's a compact muon solenoid. In terms of compactness, it's really, I would say, compact for its weight, and it's also very much a very dense detector. So it's in total 14,000 tons. And in fact, most of that weight comes from all the sections in red that you see in the muon detectors. So all of that is stainless steel that it requires 12,500 tons of this steel in the muon systems. And the reason is we have this steel to redirect the magnetic field lines outside of the magnet. So inside of the magnet, we're able to have a very concentrated magnetic field that's 3.8 Tesla. However, outside of the magnet, the field lines would dissipate if you don't have all of this steel. And having all that steel means that we can still generate 2 Tesla outside of the magnet. And I'll come back to why this strong magnetic field is necessary to begin with in just a second. But this is sort of a very quick overview of the CMS detector.
I think I would propose to look around in the control room where we are currently. And in the meantime, we got 3 very interesting questions concerning the carriers, whether people need to come here. I think this we can answer mainly at the end before we wrap up, if you will agree.
Yeah, I think that's fine.
Okay. So let's have a quick look around the control room. So this is our new control room. We have been using this control room for about a year or so, and it's a new building that was just constructed just for this purpose. And so here in the CMS control room, we have shifters 24/7. And specifically, there's 2 shifters that need to be here all the time. So we have the shift leader, who's the captain, and then we have the technical shifter, who oversees everything having to do with safety on site and detector safety as well. So one of the things I wanted to show you is, as I said, unfortunately, we will not be able to see the detector itself, but we can show you in the screens what the detector looks like right now. So these are live images from our detector. And you can see, hopefully you kind of recognize at least the colors of the detectors. And you can see among the pictures you see there are the new forward shielding, actually. So all this orange blocks that you see there are shielding for that's not really an active part of the detector. It's just shielding for the beam pipe that's coming into our detector. You can see in orange here the shielding quite nicely. And so from this images, you don't see a lot of the detector. You can mainly see the barrel shape, and then the outer sections of it are, of course, the muon systems. When the detector is closed in this configuration, ready to take collisions, of course, you don't see the inner detectors. There again, this is a very hermetically sealed detector and very dense. So when it's closed up like this, it's well, you only see the outside of it, of course. I did want to mention, however, that our detector is quite modular, especially compared to Atlas. So our detector was built into about a dozen slices. So you can take that cylindrical onion I talked about and you chop it into about a dozen slices, and we can move them, right? So when we have, basically at the end of every year, we have the year-end technical stop, and we can, if there is time, we can open up the detector and move these slices around. I can talk a little bit more about those, but you can actually see here, this is one of the air pads that we use to accomplish this. So we have to blow compressed air through these air pads, and this will lift the slices up just a few millimeters in order to help us just pull these slices. And keep in mind that this the detector taken together is, again, extremely heavy, 14,000 tons. You can imagine 14,000 small cars, and that's what we're talking about. And so even the least heavy slice is still hundreds of tons, right? So this procedure, of course, it's a very complicated sequence that has to be carried out, and so it takes quite a bit of time to do this, but it's still far more, well, let's say flexible for us compared to Atlas, where all of the components were craned down at one at a time, and then they were assembled in the cavern. So I also wanted to show you something fun here. Actually, I might just verify that we are now at 102 inverse femtobarn, because I'm pretty sure we're over. Let's see. So if we do 1,000. So this is the CMS online monitoring system website. And yeah, we have 102.4. So this is essentially this is the amount of data that we have collected in 2025. And you can see the amount of data collected as a function of time. You can see October here. And so I will do the honors and actually flip our very sophisticated counter from 101 to 102. There you go. So yeah, for now, this is the system that we have just for fun. And so in the last week, last Monday or last Sunday, we reached 100 inverse femtobarn. And so we had a little bit of a celebration. It's a nice round number. So, and yeah, so just very quickly, the other stations. So we have the DAQ station here, and it stands for data acquisition. And the shifter has to oversee everything involving the data taking. So the data coming from the specific subsystems as it is merged and then shipped off when the data has gone through all of the processing that we do. And we should talk about the trigger, for example, because after that process takes place, then the data is shipped off to the main CERN site where it is stored and distributed. And the DAQ shifter here has to oversee and make sure that all of that is happening without any problems. Then we have the trigger station here, and for the trigger, we will discuss a little bit more a bit later in detail, but essentially the trigger is our filtering system. So we cannot possibly record all the data that's being produced. We have collisions as often as 40 million times per second. And each time we record one of these events, as we call it, it's a few megabytes. So right, you can consider it about the size of a photograph on your phone. And if you collect 40 million photos per second, that's absolutely too much. But in CMS, we have, again, this filtering system, the trigger system, which is it has two stages. We have a level 1 and then a high level trigger. And these work together to filter the collisions that we have. And this process is really intricate and also very interesting. So if you have questions about that, let us know. And the trigger shifters are, of course, making sure that that process is happening smoothly. And we have also the data quality monitoring station here. And this one is pretty self-explanatory. We're looking at the quality of the data and flagging any potential problems that could happen during the data taking and responding to them. And so the crew here generally is overseeing the data taking. And if and when there is a problem, there's always some issue every day, almost guaranteed. The shifters respond to these problems and try to fix it as quickly as possible when we're collecting data. But even in quiet periods like this, where we are just waiting for the cryogenic conditions to be back in 0.6, there's still some work happening, right? So when there's no collision, sometimes we have our shifters that are doing calibrations or studying something. And even in periods like this, we can also take cosmics. We can talk about this a bit later, but we can actually look at muons coming from the atmosphere. So you have cosmic rays that shower in the atmosphere and can produce muons, and those muons, again, are just heavy electrons, but that means they're really difficult to slow down just because they carry so much momentum. So they can just slice through the Earth like it's butter, and we can actually see those muons down in our detector 100 meters underground, and we use that data for alignment purposes. But anyway, that's the kind of thing that also happens when we don't have any beam. All right, so you wanted to give Derek an opportunity to introduce himself?
Hello. So
Look in the camera, please.
this camera.
Great.
One moment.
Should go on.
Okay, I'm the other guide. Sorry, I was a little late. There was traffic in the supercar collider, but I'm Derek Grove.
I didn't tell them about it.
Oh, okay. Well, I just got here, but I'm the other guide for this virtual visit. I'm Derek Grove. I'm a PhD student living here and working on the CMS experiment from the US, and I'm with the University of Kansas. I work mainly with the pixel systems, so the innermost part. So I'll have a lot to say about that, but we'll talk broadly about everything. We have to decide, though, who's going to go.
Yeah.
So I have my boots on.
Okay, then maybe that's better.
Yes. So I'm going to be the guide that goes underground to show you the underground area. And Andreas will stay in the control room. Thank you.
Yes, usually we don't. Oh, sorry, I hear myself. Usually we don't used to. I don't used to decide who goes down. I let the guides to discuss, and actually this went very smooth.
Okay. Right. So while Derek is preparing, maybe we can go back to this, or we can also take questions. Maybe that's a good time.
We have some questions. Two of them are concerning rather the. Yeah, I couldn't open the correct ones there. Two of them are concerning the career possibilities at CERN. I think we could leave it to the last, but one is interesting. Does CMS look for extra dimensions?
Yeah, so we indeed do search for extra dimensions. So this is a little bit advanced. So it's a question that's it's basically testing some theories that predict compactified extra dimensions. So this would be very small dimensions that it's not really like, I don't know, like in the movies where you see I don't know, it's not the extra dimensions that you might be thinking of if you're watching the movies, right? These are extremely small dimensions. And so the idea here is we can deduce the existence of these extra dimensions. So we don't just make collisions and find these, right? What would really happen, for example, is if these extra dimensions exist, it could change the way that particles interact. And so that's the kind of thing that we're looking for. And in the end, we have the standard model that does not include these extra dimensions. And the standard model will predict a certain amount of interactions, or interactions should occur at this rate, let's say. And we have that prediction, and we compare it to the data that we collect. And if there's a discrepancy, it could be due to these extra dimensions. And there's other ways to do these searches, and I think some involve invisible particles that could be produced, which we can discuss as well, but we need to talk about missing energy for that.
So we could go into, but in the meantime, I see Derek is somewhere at a very interesting place. Derek, do you hear us?
Yes, I do. So before I pull it out, this is actually my personal dosimeter, and I've just inserted it into the machine here. So my dose is 0. But in some of the workplaces around CERN and CMS, you have to have this with you. And so this is again, a personal dosimeter. It measures any potential dose of radiation that I may receive. And then once per month, I have to insert it in that box. So I thought now was a good time. But also, this is what allows us access to the underground area where CMS is. So although there's tons of radiation shielding down there, we still need a dosimeter to enter that area. And it's quite interesting. This is actually linked to my biometrics. So it's linked to my retina, my iris, iris, yes. So in order to enter and then go underground, you're going to see I'm going to scan this. It will allow me in this first little room here. And then I have to scan my eyes. And if my eyes match my dosimeter in that device, if my eyes match my dosimeter, then the next door will open and I'll be allowed entrance into the underground area. So let's go ahead and make our way underground. And you may hear it talk to me while I'm in here. We'll see. So everything's good. And now Naomi will come with me. And Naomi will give you kind of your perspective as you were going through this, as if you were going through this. So then you must look into this box. And if everything's good, we're allowed access. So now we're going to take the elevator underground. If there's any other questions, we could take them because we're probably lose connection while we're going underground. But this elevator goes all the way down to CMS, about 100 meters. So right now it's at 97 meters underground. And I'm going to call it, so it'll come up and we'll catch our ride down. This elevator has its own oxygen supply, its own power supply. So it's one of the safest elevators in the world. If there was ever an emergency, we'd take it up rather than take 100 meters worth of stairs. But yeah, I think we're just going to enter. If there's an opportunity for Andreas to say any more or answer questions, I'd like to give it back to the control room. And then once we're underground, we can talk more. So.
All right, thanks a lot, Derek. So I maybe can answer 2 more questions. And I think we'll also discuss a little bit more about CMS. So we had an interesting question about what, and maybe before you get into the elevator, you can answer it quickly. So the question is about what kind of computers people use and what kind of brands. I've seen many Apple computers. People have Macs a lot. Otherwise, you get all kinds of computers. I don't know if you have an interesting computer you want to share with us, Derek.
I mean, I personally use an Apple. A lot of us run Linux, yeah.
Yeah,
so
exactly.
Our
server farms run Linux.
Yeah.
Sorry.
yeah. But Mac and Linux, not too many Windows. I think that's the only caveat. All right, we're going to take the elevator down and probably lose connection now. But we'll see you 100 meters underground. And we'll try to show you as we go down. We will try to show you for as long as we can our descent, because it is quite a fast elevator. Your ears usually pop a couple times on the way down, which is pretty strange.
Yeah, so just to maybe you didn't catch what Zoltan was saying. So back to the computer. So many people run Linux, and basically all the servers are Linux servers. And so very few people are using Windows, I think. But there's some machines that require Linux. So for example, for the DCS, I think that's in Windows.
The main path is Linux here, but not just because we are so nerds that we cannot tolerate anything else. Some of the hardwares require Windows.
Yeah.
In the industry, the Windows is a little bit more widespread than the Linux. And obviously, we are not completely independent from them. So some of the hardware really likes Windows as well.
Okay.
They are almost down.
Yeah. Okay. So I think we never lost them. Maybe. I didn't
Or
notice.
we just didn't recognize. I don't
Yeah.
know.
So okay, Derek, do you want to take over again? You're muted now, but
Yes.
Okay.
Yes.
Right.
We can show a bit now, and we have some interesting things to show you underground. So we're now about 100 meters underground. We're slightly above the 100-meter mark, but that's because there's multiple levels down here. So we're on level -2. And so I like to think of this next room as kind of like the brains of CMS. It's a lot of the readout electronics associated with the detector. So if the detector is kind of like the nervous system, or it like feels the particles, then this is the room where the first kind of interpretation happens. Some of the triggering, as we talked about, the decisions on what events to record. So we'll make our room, well, we have to pass through first this room, where we can see the 100-meter shaft that we just came down. And so the light just kind of symbolizes, data going back up to the surface from down here, data from the collisions and our experiment. But now, as we enter this next room, we'll see some of the readout electronics of CMS. So there's a lot of complicated electronics that go into this experiment. Probably some of the most advanced is the triggering, or the electronics associated with the trigger. So we have to very quickly be able to decide what events we want to record, kind of like write to a hard drive almost. And so some of that electronics is in this row here. If we can see. And so Andreas mentioned some numbers earlier, but when we're running at peak collisions, we're doing about, I think it's an order of like 2 billion collisions per second. Somebody can correct me if my numbers are off. But although we do about 2 billion collisions per second, we can only record maybe about 10,000 of them. So we have to pass through a couple of these triggers to decide which collision events we save, and then we'll analyze later. That's okay. And then, but we also have other electronics in here. So if we go down this row, these electronics are related to the readout of the pixels. So these boards here are called the pixel feds, front end driver, I believe. I just know them as the feds though. So the cyan wires that are kind of going into them on the bottom, those are fiber optic cables, and they're coming right from the detector. So since we have this ultra strong magnetic field inside the detector, we'd like to convert some of this readout data to optical signal, to light. It's faster, but it's also, if it's transmitted on a fiber optic cable, then there's no interference from the strong magnetic field. But regardless, these are some of the boards that are crucial for reading out the innermost part of CMS. And to give you kind of an idea, the day-to-day of some of the shifters that we saw upstairs, the more expert shifters, if there's a problem with one of these boards, it can just kind of happen all of a sudden, and you have to come down here and replace one. So it's very, it can be a little chaotic at times working on this experiment, because you never know what's going to go wrong. And Andreas, very accurately said it's a day-to-day thing. And yeah, you just have to have people that are on shift and prepared to handle these problems. How much, huh? Oh, we have about, the number of pixels we have in CMS right now is on the order of 200 million. So there's a lot and a lot of data coming out of this subsystem. And this is just the innermost part of CMS. So yeah, we're handling a ton of data, and it's coming at us constantly as we're doing these collisions. So all of our electronics need to be in working order, because we don't want to waste any of our time running this big experiment. So we're going to make our way to the next area. I don't know if there's any other questions or anything the control room would like to say for now.
Yeah, at some point we can maybe take more questions. Are there any interesting questions at the moment?
What is your favorite theory on or ongoing experiment at CMS?
So the question is whether we have a favorite theory or ongoing experiment. And of course, we have to say CMS. It's the best one.
How
We're
many
not biased at all.
channels do we have?
Yeah.
More than 200, I guess.
How many what, sorry?
Search channels.
Yeah, I mean,
Yes, channels.
much, yeah. I think on the order of hundreds. Yeah, I don't know. A favorite theory, I have to think about this, but yeah, Derek, if you have something, feel free.
Well, my analysis, we're looking for supersymmetry, which is an extension of the standard model. If you were to, and supersymmetry, it gets very nuanced, these new theories in physics, because I say supersymmetry as if it's one theory, but it's actually a plethora or a handful. There's so many supersymmetric theories.
Yeah,
it's almost
it's a property of the theory, right?
Yes.
A theory can be supersymmetric.
Yes. And so I can't say it's my favorite theory, but it is what I'm working on. So I am interested in it. But yeah, we're always looking for new things, and there's a lot of theories, but where our field is at, actually, we don't really know the direction to move. We have some great theories, and we're looking some extensions to the standard model is what I mean by theory, but we're looking in our experimental data, but we still have yet to find anything concrete enough to push us in one direction. And so, we're working really hard, but this is kind of where we're at. We're really trying to find something to push us in a new direction.
If I can just quickly add,
yeah.
So they asked about favorite experiments, and I don't know, there's two interesting ones that come to mind, and it's also to give you an idea of everything that's happening at CERN, right? I mentioned the antimatter decelerator earlier, and they have an experiment called the Alpha experiment, and they recently published a result that's super interesting. So basically, they produced anti-hydrogen, as I mentioned before, they are able to do this routinely at the antimatter decelerator, and they produce a lot of anti-hydrogen, and then they basically let them fall, if you will, and they were checking whether they would obey gravity or somehow not. There's no reason to think that anti-particles would be anti-gravitational, but nobody had tested it, and they tested it, and of course they behave just like normal, regular.
There are some theories that the gravity is a little bit more complex than what we know today, and in this case, still the anti-hydrogen would fall, but would fall with a different G constant, and that's what they tested.
Yeah. So that's just an example of a very, very interesting result from a totally unrelated experiment to CMS. Right, back to you, Derek.
Oh, thank you. Yeah, and they're also doing some experiments on transporting antimatter here. If I remember correctly, we have a truck that can drive antimatter in a container some distance. It's not as, I kind of prefer the gravity one, but this is some development. There's a lot going on with this antimatter factory here. But yeah, so I wanted to kind of point out this picture. So this is a bit of a historical account of these different accelerators that we've had here at CERN over the decades, actually. So we're always building bigger rings. And, if you're wondering why that is, it's because we're always trying to go to a higher collision energy. And but why do we want a higher energy? If you remember Einstein's equation, E equals mc squared, the types of particles with their mass that you can produce, it depends on how much energy you have. So if you have more energy in your collision, you can produce more massive exotic particles that then we can watch them decay and study them here. So all of these accelerators are not in use anymore, as far as I know, except for SPS, and Andreas can correct me, but I think LINAC 4, one of the LINACs. So the reason these ones are still in use is we actually use them as part of the injection to the LHC. So the LHC is the biggest ring. It's our flagship accelerator at the moment. But we still use some of these older ones to kind of prime the beam, to get it up to their energy, and then inject it into the LHC where we can accelerate it to the maximum energy of the LHC, which is, yep.
Yeah, I was
Go
just
ahead.
going to say you can think of it almost like the stages of a rocket, right? You know, when you're launching a rocket, there's several stages. So it's a bit like that. Each of these accelerators gives more energy to the protons. But also I wanted to mention that they are also in use, or they service fixed target experiments. And so both in the proton synchrotron and superproton synchrotron, there's experiments, some of them short-term, some of them long-term, that receive protons. And as an example, in the PS, we have the cloud experiment, where they have a chamber where they can simulate certain layers of the atmosphere. And then they look at how the protons interact with those. And so it's a very, very interesting experiment, again, unrelated to the LHC and using the beams from the PS.
That's very interesting. I actually didn't know about that experiment. It's called Cloud?
Yeah, cloud experiment. Yeah.
That's cool. Okay. But yeah, and there's some numbers down here towards the bottom that kind of put into perspective, the increase in energy, but also if you want to measure it, the percent speed of light of the beams and the accelerators. So as we go up in speed, closer to the speed of light, we're actually going up significantly in energy. And this is an interesting, you may notice, by PS, we were at 99.93% the speed of light. And then SPS, we're only marginally closer, 99.9998, the speed of light. This is an interesting consequence of Einstein's theory of relativity. Anything with mass, in our case, the protons or electrons, whatever particle we're accelerating, anything with mass can never go at the speed of light. You can keep adding more energy to it, as we do here. Each time we build a new accelerator, we're putting more energy into the beam, but we're not really getting that much closer to the speed of light. We are, but only marginally. So it's very interesting. But yeah, so right now, the energy of the two beams in the LHC, they're rated, or the LHC was designed to do up to 7 TeV. This is 7 trillion electron volts of energy in the beam. An electron volt is a convenient unit of energy for us. But yeah, right now we're at 6.8 TeV per beam. So
maybe
we
I
also,
can,
yeah, go ahead.
sorry,
add
maybe I can add a little bit to that. So this may not be, I think it's not immediately obvious, but the limitation here, right? When you want to reach higher energies, the limitation is actually the bending magnet that keep the magnets, these are called dipole magnets, they bend the protons and keep them inside of the LHC ring. You can see a picture here. So if you want to give more energy to the protons, you need a stronger magnetic field. And so there's 1,232 of these dipoles, and they don't have identical behavior. So the way they work, it's an electromagnet and it's superconducting, of course. And in fact, it has to run at extremely cold temperatures because it requires superfluid helium. So these are extremely sophisticated devices. But again, not all of them have the same behavior. So some of them, when you inject the amount of current necessary to produce the magnetic fields that are required, they might trip, if you will. So they might quench is the proper term. And so a few of these magnets are not reaching exactly the currents that are needed to reach those magnetic fields. And so that's where we're at 6.8 TeV instead of 7, basically. And maybe just another quick thing, right? So you mentioned we're not really, even if you increase the energy, you're not getting much in speed. But we're basically already essentially at the speed of light. Like the protons are traveling 3 meters per second shy of the speed of light, right? So you take the speed of light, 299,792,458, you subtract 3, and that's the speed of the protons. Another way to think about it is they circulate or orbit the 26-kilometer ring 11,245 times per second, right? So essentially the speed of light. All right, back to you, Derek.
Thank you, Andreas. The magnets here, as I was told, they were a big innovation, these superconducting magnets. No? Like they built the LHC tunnel, but it took them a bit longer to pin down this technology of the two magnets side by side. So I was told. I'm not a magnet guy.
Yeah, I'm also not an expert, but there's a lot of interesting history there. And the design of the magnets themselves and the fact that they had to build so many really influenced the design of these magnets. So it's all super, super interesting. I'll just mention, since we're talking about magnets, that in the on the horizon, we have an upgrade that's planned. So we're going to have collisions for the rest of this year, and then for, let's say, half of next year. And then the LHC will stop for several years, at least until 2030, to upgrade the accelerator and upgrade the experiments so that we can reach higher luminosities, which means we have more, the rate of interactions will be radically higher. And in order to accomplish this, for example, we need a different kind of magnet technology, superconducting magnet technology, to be deployed for the magnets that squeeze or focus the beams before the interactions. So we will have to go from the superconducting material. Right now, the most common is niobium titanium, and this will require the one of the first applications of niobium tin, which is more difficult to work with. It's a more brittle material, but it can produce higher magnetic fields, and that's a requirement for this next stage of the LHC.
Yeah, there's almost too many upgrades to count going on with this high Lumi upgrade. I would like to learn more about the beam side of things. All right, but we can show now we're kind of at the end of the tour in the sense of how far we can go. So right through this door is where the CMS detector, or where you would get to the CMS detector. So there's a hallway that then leads to the experimental cavern, but we obviously cannot go in there right now. So there's another safety mechanism here, as you see on the camera. It's kind of like the doors that we first went through upstairs, in the sense that you have to also have your dosimeter and then scan your retinas at the same box. However, there's some additional concerns here. You have to take a key. Normally, these would flip down, and there'd be some keys in there that you take out, and you take the key with you into the experimental cavern. And the caveat is the entire LHC cannot turn on until that key is returned, and then it's flipped shut. So there's a lot of safety contraptions that we have here, but it's for a good reason. We don't want any accidents, and we want to keep everybody monitored and only in places that they should be getting access to. So although we can't physically go into the chamber with the CMS detector, there is a part of the CMS detector that reaches us out here, and that would be part of the super strong magnetic field. So we have a 3.8 Tesla magnetic field in the CMS detector, and we have that to kind of bend the trajectories of the particles. But with that being such a strong field, this far away from the detector and through the walls, there's still quite a strong field. And so if you have anything that's magnetic with you, like these paper clips here, they react to the field and they try to align themselves with it. And this is probably the best part of our tour here at CMS, but we have a lot of these paper clips everywhere because they're all just magnetized, even this far away from a CMS detector. So I've also brought some additional paper clips with me because there's some other interesting things you can see. So they are already sticking together coming out of the crate. I'll take out maybe this many. Okay. And if I just kind of throw them down here, they all kind of stand up. And again, they want to align themselves with the direction of the field. So CMS is quite well known for the solenoid. It's in the name, CMS, Compact Muon Solenoid. It's the largest solenoid in the world, as far as I know. We built it quite a while ago, and I heard stories there may be a bigger one somewhere now, but I haven't confirmed it. So
Yeah,
I still think we have the
ITER,
biggest solenoid.
yeah, ITER is going to have a bigger solenoid, but I don't think it's under construction. I
Sure.
don't know exactly what status.
For now, we still have the record.
Sorry, one.
So actually, what we know that this is the biggest solenoid with this field.
Mhm.
That's something that we can claim for. Maybe, well, even the synchrocyclotron solenoid was something in this size, a couple of centimeters difference in either way, I don't know. And that was built something like 70 years ago.
Yeah.
But of course, the field strength was completely different. Also, there are some other magnets, superconductive magnets, that can go beyond 10 Tesla. Even the dipole magnets that we are using in the LHC go somewhere around 10 Tesla. So there are stronger magnets. Maybe there are bigger magnets, but this is the biggest with this field. That's absolutely true.
Yeah, I think that in terms of a stored energy in the magnet, it might be one of the largest, if not the largest,
Well,
in terms of stored energy.
Exactly. That is related to the volume and also the field. So
Exactly.
there are some urban legends about that that the energy that we are having in the magnet stored is something like around 2 gigajoules. So something really strong. What I heard about that this is somehow comparable to the kinetic energy of Boeing 747. So
yeah,
and
well,
we all know how much it can deform the landscape once it crashed down.
So I remember reading that it's enough energy stored in the magnet to melt something like 40 tons of gold, but I don't remember the exact number. It could be 40 or it could be 400. I don't remember.
Yeah, exactly. But what underlines this, that, or what this indicates, that we have to have a very special and very fine-tuned safety mechanisms, bring this energy out of the magnet once something fails. And yes, we do have it.
So we don't have too much time left, so I wanted to take an opportunity to answer a few more questions.
Sure.
So we have a question asking, in terms of storing mass data, how do we store all these petabytes of information, given that basically we have so much data coming in, and how do we store them, right? So I will mention a few things, right? So again, we have this filtering system that we are running at maximum capacity, maximum bandwidth. So we're taking really as much data as we possibly can with the current system that we have. And so we, as I mentioned, we transfer that data to the main site in CERN. So this is really cool. You guys are now in the under the racks. Do you want to say a word, Derek?
Yeah. So the room that we walked across or through earlier, we're now underneath it, directly underneath it. And so you can see a lot of these cables. I mentioned there's multiple floors. A lot of these cables are what is running out of the chamber, the experimental cavern, and
so
interfacing with.
So maybe you can show these red cables specifically. So these are for one of our muon detectors, the resistive plate chambers, and each of those red cables has multiple cables inside. But anyway, each of them carries a few kilovolts. So
these are high voltage.
These are very, very high voltage cables.
Here, these.
Also, what you can see here is that all of these, we didn't mention this, but there's a wall separating the experimental area where the detector is from the service cavern or the counting room that that Derek is in right now with Noemi. And so we have to route the cables under this wall, and it's really this wall is 7 meters thick of reinforced concrete. We'll just very quickly show an image.
Yes.
So you get an idea of what we're talking about. But this is why the routing is very intricate here. So what you're seeing here on the screen is I'm trying to show with the mouse the service cavern, and this PM54 here, that's the elevator that Derek and Noemi took. And right now they're under this this volume, this area, which is the service cavern, and then this thing here called the pilier, that's the wall that I'm referring to. And so again, these cables have to be routed around the 7 meter thick concrete wall. And then the main experiment, the main detector is on this other side, the experimental cavern. And this PX56, that's the main shaft down through which the detector was craned down one slice at a time.
Actually, one very important role of this pillar is to keep the two underground caverns safe. I mean, so the rock around is something very soft. What we have, molas and some limestone stuff.
Okay.
That means that if you would excavate these two huge caverns, you can see that one of them is almost 85 meters, the other is 55 meters. You might imagine that's a huge amount of soil or rock that you remove. The two wouldn't be able to stay like this. So this pillar helps.
It anchors them together, basically.
Exactly, and also keeps the roof. But on the other hand, the side effect of this wall is that this acts as a giant radiation shield.
Mm-hmm.
So that allows us to walk always in the underground service cavern, as Derek is doing right now.
Yeah, in fact, it's the only location in the LAC where we can have visitors access the underground areas
Even
where
during beam.
even when we have beam. So if you come visit the LHC, you can check out the underground areas, some of the areas that Derek and Noemi, but you can't go under the false floor, for example. Right. So I think as Derek and Noemi make their way back, we can maybe to wrap up
we have a before they come up.
Yeah.
We have a philosophical question.
Okay.
That I think when we figure out what the rules of the universe is and what the entire universe is made up of, what comes next?
Then we go on holiday.
Yeah, but this holiday is pretty far, I guess. So,
well, yeah. I mean, there's one way that I would answer this is that's not how this works. We don't. There's no situation in which we figure everything out. The way I see science is as a description, a model. It can help us predict the outcome of certain experiments, and it's a way to view the world. We say the world is made of atoms and this and that, but in 50 years we may have, and that's what we work towards, a better model. We always try to improve on the model. But fundamentally, we cannot ever answer what is the universe made of. This question doesn't ever end, right?
This is a philosophical question.
Yeah.
There are some philosophy schools that state this, and other states that. But what is important that all the models have their validity range, and what we know. sorry of my voice. What we already know that we are really not at the end of the story. The gravity is somehow cannot be fitted in the current theories, and what we expect that it would be, the universe would look like really different at the Planck scale. Fortunately, to create a Planck scale accelerator would cost a little bit of a, I would say, a challenge. With the current technology, its size would be something like the solar system. I don't think that we could apply for grants.
Exactly. So yeah, I mean, there's different ways to view this, but what I would say is that even if we get to a point where we have satisfactory answers with heavy quotes to most of the current mysteries, um, you still can test them. You still can challenge these models and just test the prediction that they, right? So you can have a model and it says should be the outcome of this experiment. You can keep that testing that, and again, there's the question of ranges of validity of these theories. So anyway, just interesting question that we could talk about for a long time, but yeah, thanks for that.
Yeah. So finally, Derek is back. I think before we wrap up, the two questions that I postponed to the last, it should come. One is that how is the process to work at CMS, and what kind of careers are available for those scientists that are not able to go to Switzerland? I think that's quite an important thing. Or you can only be connected to CMS if you go to Switzerland physically.
Right. So there's a lot of opportunity to participate in the CMS collaboration. And
exactly.
Yeah, and of course, the most traditional way I would say is you study physics and you basically collaborate with a group, typically in a university. There are in the US many universities that have groups that participate and in the CMS collaboration, but also the Atlas collaboration and so on. And that's, I think, the traditional route that you can take. But there's many programs at CERN, for example, like even for high school students, there's the Beamline for schools, or the Beamline, what is it called?
The Beamline for schools, the B4S.
Yeah.
But also this links to the first question in the queue, that I've heard that CERN provides applications for international internships to shadow engineers for high school students. What qualifications need to be met to meet the expectations and have a chance to being accepted to these internships? I think this is somehow linked to the
Yes, it is. Unfortunately, I don't know off the top of my head what specific programs there are for high school students and what is the eligibility like. But the Beamline for schools, I know that schools can apply to it, and you basically submit a proposal, and if you are selected, you do an experiment at CERN, right? So they give you beam time, and you just do whatever experiment you proposed. So
actually, DAISY is also in this game now.
That's
so
cool.
It's one team will be selected for CERN, one team will be selected for DAISY. This is one of the coolest things. I think the next round of applications starts sometime in January. It's worth to look at the web page.
Yeah, so then I don't know too many. So that's one thing you could look into, Beamline for schools. And so another is, this is for university students, but undergraduates can apply to the summer student program at CERN. And that's something that I would highly encourage. And another thing I wanted to point out is that this doesn't it's not necessary for you to study physics, right? We actually have many students that are selected for the summer student program that might be computer scientists or might be engineers, of mechanical engineers, electrical engineers, and so on. So I also, if you're interested in this, you don't have to pursue physics. You can also, pursue computer science, for example, and still apply to some of these programs.
We also have administrative students as well.
Yeah.
So
that's true.
It is not just linked to science in the sense.
Exactly.
CERN is a huge establishment. Actually, we accept quite a lot of different skills. We do need quite a lot of different skills.
So there is one more question, Zoltan?
This was this one, and actually we have quite a lot of more questions.
So I guess.
Yeah, but I think maybe one more, but then I think I want to respect your time, and you all have been very generous, and I appreciate that.
The windows we have already done. The extra dimensions we already done. That was something. As the data travels through all of the electronics, do we lose signal or increase noise? That's a very interesting question.
It's an interesting question. There's probably a few different answers depending on who you were to ask it to. What I can say for the pixel side of things is for this upgrade that we talked about, my university is making all of the electrical link cables that go, it's like the first transmission line of the data from the pixels. It's from the pixels to the module that will then convert it to optical fiber. And what I can say is these cables that we're manufacturing, we have to test to make sure that they only, at worst, they do 1 bit flip in every, it's like 10 billion bits or something. It's like a ridiculous number. So that's like a metric that we're targeting for these cables, and they all have to pass the same test. So at least for the pixels, yes, it could happen, but
yeah, these are, I mean, again, there's many ways to answer this question, but one of the reasons that this could occur is some of the electronics, right, that some of the detectors have electronics on them and they're exposed to ionizing radiation. So that's one way that you could have this kind of data corruption of some sort. But of course, yeah, I guess I would generally answer to say that we collect a lot of data and as much data as we can. And so at some point, if there is some kind of event that we collected and recorded, and there's obviously some kind of a problem with the data, we will, it's very likely that we throw it away. Let me also add to that, that when we are studying these interactions, right, I'm thinking of like you can have one event where the data is corrupt and it's telling us that something impossible has happened, right? In a worst case scenario, we have one event where the data somehow got corrupted and it looks like some new physics. Well, it turns out that one event is not enough to draw any conclusion, right? We take all this data because in order to have a result, we need to study a large volume of data and have enough statistics, as we call it, to draw a meaningful conclusion, right? So I don't know, I think that's also relevant for this question.
No, it is.
And actually, this brings up something else as well, that we have a very good simulation of the detector as well. So we are not just collecting data, but we have a virtual detector indeed running on our computers.
Yeah. And this is very detailed, right? We have to simulate how any given particle can interact with any material in the detector, right? So if we have brass in the detector, we have to simulate that interaction. If we have, I don't know, silicon detectors, we have to simulate that. Fiber optics, all of these materials, it has to be taken into account. And that's why it's also important to know where everything is inside our detector. So we really, when we say we compare the data to a simulation, the simulation is as detailed as it gets. We simulate the collision itself and we simulate how the particles that are produced interact with every part of our detector.
That's where the physics comes in, the theory.
Exactly. Yeah, that's how we can improve as well.
That's how we check the theory. We simulate how this theory would look like in our detector, and then we take a look at. That's a very important thing. All right.
Okay. Thank you all very, very much for the tour and for being so generous with your time and answering questions, particularly on a Saturday evening in Switzerland. I can't thank you enough for everything you've done, and I really greatly appreciate it.
It's our pleasure to participate today.
Oh, wonderful. Well, so I think this concludes our session. Thank you again to everybody for being on here on a Saturday morning here, Saturday afternoon or evening there. Yeah, thanks again.
Thank you very much for the very positive feedback that we also got through the chat. All right. Thank you. Have a nice evening.
Wonderful.
Ciao, ciao.
Bye.
Ciao.